Thank you for the introduction. As said, welcome to my talk about silicone sealants today. I will talk about silicone sealants tested in the unaged and in the chemically aged state. As said, I'm working at Dr. Siebert Consulting Engineers, and during my master thesis I had the opportunity to do tests at the Bundeswehr University in Munich, Neubiberg, at the chair of Professor Siebert. Today I will give you a short introduction about the material I tested. Then I will talk about the unaged material. I did some tests to have an idea of the mechanical behavior. And then I artificially and chemically aged samples and tested these with methods I will show you. So starting with a short introduction, here we have polymer plastics. You can classify polymers in according to different characteristics. Here I have chosen the mechanical thermal behavior. On the left you can see a duroplast. It's a brittle, hard material. And as you can see, it's closely cross-linked. If you harden it once, it's very stable in high temperature. As the example shows, for example, you can perfectly use it for a fireman helmet. On the right-hand side, we have thermoplastics. They are non-cross-linked, and as the name already says, they are thermoformable. An example is a Lego brick, or also the intermediate foil of laminated glass. It's also an example for thermoplasts. And finally, we come to the middle, elastomers. They are widely cross-linked, and the strength is relatively low, but the big advantage is that you have high possible elongation rates, and that's one of the reasons why it's perfect to bond metal parts with glass. And as you can see here in the example underneath, here we have a detail of a structural sealant glazing facade where the glass is bonded onto the metal structure. Just one slide about the behavior of the material. Dependent on the temperature. Here you have the three types of polymers, elastomer, thermoplasts, and duroplasts. It's just a qualitative slide, but you can see they all have one in common. They have a huge stiffness drop at a certain temperature. That temperature is called glass transition temperature. And what I want to show with this slide is that elastomers have this temperature drop at a very low temperature, which is very nice for applications in civil engineering, because you have a huge range of temperature where you can use the material, and the stiffness is not constant, but it's not varying and not dropping that much, so you can work with it very good. Dimensioning silicone is always an important topic if you construct something with silicone sealants. And I think most of you will know the ETAC 002. That's the state-of-the-art dimensioning. It's very simplified, and it's for standard situations. You just take the impact, divide it through the area of the bonding, and then you get a stress center called here, and then you compare it to the resistance. And why I tell you this is I want to quickly talk about sigma des, so the resistance of the sealant. You get that if you have the resistance and divide it through gamma tot, which is mostly 6, so relatively high. And that number, like a safety factor, is set together with different components, and one of these components is also aging. And of course, it's always, as an engineer, you always want to calculate more detailed and not having just big numbers of safety factors and hope you are on the safe side. And what I did artificially age silicone sealants, maybe to find out more about that material, and on the long term, maybe if you do this for more components of gamma tot, you can get a lower number for that. And there are also applications where you can't use the ETAC 002, and also for chemical aged sealants, you can't use the ETAC 002 if standing water cannot be avoided in your facade. For example, if you have a horizontal joint and water can stand on it. So I had my samples. Firstly, I had dog bone samples and did tests. Before I started, I wanted to know about the material, and I started with unaged specimen. And here you have the rheological, a rheological model from elastomers. You have the basic elasticity, and you always have a part of viscoelasticity that is time dependent. I started with basic tensile tests, testing the behavior and fitting material model. Of course, if you want to really describe the material, you should do more tests like tensile, but as this was not my focus, it was okay for me to just do tensile tests and also describe the viscoelasticity. This I did with dynamic mechanical thermal analysis, DMTA. You can see it's a huge machine and a really small sample. On the right picture, you can see the sample in the machine. It's only 20 millimeters high, and I cut it out of a bone sample. What you do is you have different frequencies as impact, and you have these frequencies at different temperature stages. So starting at plus 70 degree, going down to minus 100, and then you can tell how the material's behavior is at different temperature and also different frequencies. If you then use the time temperature superposition, you can, with this data you have measured in a certain area of temperature and frequency, and if you put all these together, you can get master curves, and then you have a stable curve where you can, for different temperatures, so you have different curves for different reference temperatures, and you have the behavior of the material depending on the time or the frequency shown very nicely. So now I only had unaged samples and described the material, and the question was, can I use that material also for aged samples? For example, I'm building something, gluing a glass on a metal structure, and then it's standing there for 20 years. And at the moment, we often assume that the material is kind of the same because we are dimensioning it with the material model we have. And of course, we use safety factors and hope they have everything in we don't really know about. My idea was maybe if I age samples chemically in liquid solutions, the edge area will show differences, and the center area is still the unaged material. And maybe it's more realistic to dimension sealants with a cross section in the middle that is still the material I have, and maybe the material in the edge is damaged, and maybe I can leave that out of my dimension. But then also reduce the safety factors I use. So what I did, I had samples, cylinder samples. You can see here, the basic sample was 30 millimeters high with a diameter of 15 millimeters. And I aged these and then cut out smaller samples for the different methods I used. The medium one is 8 millimeters high, and I took that for microcomputer tomography, and the really small plate is only 1 millimeter, also cut out precisely, is for infrared spectroscopy. I will show you on the next slides. And the artificial aging was based on ETAC. There are aging processes described, and I used distilled water at 45 degrees, saline solution and sulfur solution, which should simulate acid rain, and also the concentrations I took out of ETAC 002. The duration I could also use, based on the ETAC. I tested these samples for 42 days, and of course I wanted to understand the process during the aging. That's why I chose 12 days where I tested the samples and always checked. Of course, I also checked unaged samples and tried to check if there are differences with my chosen methods. So now finally we come to the methods. Often you do aging tests and you have mechanical strength before and afterwards. Then you know, okay, maybe it's 10% less, but you don't really understand why, and you don't understand what happened in the material. And my idea was to make that visible with microcomputer tomography for describing my first method. It's, most of you might know CT, computer tomography from medical technology. There you have humans as samples. The only difference is we here have very small samples, and the resolution is a lot higher, which is very important, because if we have a small sample diameter 15 millimeters, we need a high resolution to find out changes in the sample. Then you have irradiation of the sample, and then you have density information of the whole, all the sections you do, and with the computer you can reconstruct these sections to 3D models, as seen here on the right next to the colored picture. The challenge here was the sample itself, because normally you test, for example, cellular concrete. There you have really different density in different areas, but in my case the material is very homogeneous, and even if something changes, you can't expect the density going up or down very high, so you have to calibrate the machine very precisely. I did that with a highly aged specimen that I aged in highly concentrated sulfur solution. And in the end, you can see here on the left corner, I could see differences in the edge area and in the center area. Then I took my actual samples, putting in these solutions based on ETAC, and I tested several days and over the 42 days, but I couldn't see any changes, which is good for the material. But yeah, I couldn't use my my dimensioning model I thought about. So I thought maybe I will extend the test and do it for 100 days. And also after 100 days, there was really no changes. That's why I also increased the sulfur solution, the concentration of the sulfur solution, and then I had changes, but it was like 100 times the sulfur solution I had I used initially from the ETAC. So with these results, I wanted to do the same with another method. and I used infrared spectroscopy. Here you measure the transmission, so you have infrared rays, and you can measure the transmission, and you can really tell about the detailed chemical composition of the material you have. So I thought if there is something changing, I will also see something there. You measure a really small point, like 0.5 millimeter, so you have to measure over the diameter several times to see if something is changing. And of course, you always have the unaged and the aged, and then you see if there are differences. And luckily, I had the same results here. Also, over the 42 days, there were no changes, so the resistance is very high of my tested material. And also over 100 days, no changes. But I've seen changes with the samples aged in high concentrated solutions. So comparing these methods, they fitted very well, which is very nice. Yeah. And as a conclusion, I can say the aging resistance was very high of my material, higher than expected. It seems that the chemical aging doesn't really destroy parts of my material. And what I also with the higher concentration sulfur solution, I've seen that the aging is not homogeneous over the cross section, but it's more in the edge area. And maybe if you have a safety factor for that, it doesn't make so much sense because it's dependent on the cross section. If you have a big cross section, the influence is a lot lower, and maybe you have a safety factor too high. Here I have a 3D model, and just to show you from microcomputer tomography how it looks like. I'm cutting through the sample. And here, this is the really highly aged sample. On top, you can see the differences in the edge area and also in the center area. So yeah, that was it. Thanks for your attendance. If you have any questions, I think we have some minutes. Thank you.
Thank you, Mr. Gast. Yes, we have 5 minutes for discussion before the coffee break. Other questions?
Thank you, Florian. That was a wonderful presentation. Part of the degradation process of a cross-link material is a concern for the actual cross-links going away. So you're getting like chain scission or the polymer bonds. Did you consider any techniques to try to evaluate if like cross-link density and how that changed over time?
Yeah, with the as I said, over the 100 days I tested, I couldn't see any changes, but with the really aged samples, I have seen that the filler goes out and water can come in. So that's the nice about the infrared spectroscopy, that you really can see the chemical changes. And I could see, okay, parts of the filler are going out, and the density even was higher afterwards. And that's why because of water came into the sample.
There's another question.
Yeah.
Did you make the DMTA testing also with the aged material?
No, that's something that would be really interesting, but yeah.
More questions?
Yes, good morning. So from your testing, can you see that there's any feedback regarding the current safety factors that we're using for structural silicon design? Because currently is about 6 according to the ETAC, and some suppliers tend to push it down to like 4 for certain projects. What's your kind of feeling on this one, having done all of the testing on the artificial aging?
Yeah, the problem is with the 6, as I said, is set together of different components, and no one really knows. You can't find how, there is no real documentation how they are set together. So it's difficult to say, okay, this and there are also different types of aging, and you can't say the chemical aging was 1.5, and that's kind of the problem if you yeah, take this factor and take it down. But of course, with my results for this specific material, I can say that the chemical aging doesn't damage the material so much. And yeah, I think in the end you have to check different types and all the components that lead to that high factor. Yeah, and the goal is to bring that down, but to understand more what's going on. I think that factor is also so high because some, yeah, super simplicities, and yeah, we are calculating something we don't know all about.
Okay. More questions? There's no questions anymore. So then thanks again, Mr. Gast.
Thank you, Mr. Schneider.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!